Somebody was having issues with it. I'm not sure what was going on. Yeah.
I need to
Well, I have balloon on. I'll think I'm
try to
I don't work at anybody.
And it's a PDF, so there's no.
Yeah, it should be staged.
Oh, yeah.
I hope you had a good time to look at the posters and coffee up a little bit for the next talk. Bye.
Shall I just go ahead and start? Okay, perfect. I am just going to keep my timer here so that, all right. I am so extremely psyched to be here. Thank you so much for having me. I feel like workshop that happened about 18 months ago here that John organized had a big part to play in like the stuff that I'm going to talk about today. So it feels like a homecoming of sorts to be able to talk about this. Before I jump in, I also, again, I'm very grateful for all the people who did the tutorials yesterday because that set up a lot of the vocabulary that I want to refer to here when I say things like RAG or...
Oh, it should be on. Is it not working?
No, it's very late.
Can folks hear me now? No? Do I need to be very...
And that they can. Is it just in the room? But they're not getting it.
Interesting. Should I just talk louder? Will that help? Okay. Yeah.
It's not for in here, it's for online.
Okay. Yeah, so I guess just project as well.
Oh, so this one's just for the online thing.
And can folks in the back of the room hear well? Is it a possibility to turn up the volume in the room?
We generally can't do that, but you
If
can
I
be a
use
lot
this,
louder.
does it help?
You could be just louder.
Yeah, I'll just be louder. All right.
We'll restart your time.
No problem. All good. All right, so huge thanks to people who did the tutorials yesterday. I'm going to be using terms like RAG, which stands for Retrieval Augmented Generation, or embedding spaces, and I'll do a very quick intro, but if you all want to know more, go look at those tutorials or talk to the people who organized them. They were really, really fun. Okay, so what I want to talk about today is something called an embedding space that is an integral part of how a lot of transformer models and other machine learning methods work, and in particular how we can use them to do all sorts of interesting things in astronomy research. So this talk's going to be divided into roughly 3 parts. Part 1 is what got me started into this whole business. So I've always been interested in this notion of how we search and keep up with the literature, right? Like, and as an example, there was a recent press release. Well, it was recent when I made this talk first. Press release about this disk galaxy that people found at extremely high redshifts, like redshift 7, where we were like, whoa, how is that even a disk? And so I read the thing, and I'm like, okay, I want to know what this is based off. Now, a well-written press release will have an attribution to the paper, but sometimes you don't get the press release. You see something on social media, and so you're like, how do I find this paper? So if it's linked, you can go back to the actual press release by NASA or ESO and look up the paper and find it and be like, oh, okay, that's the study. Or if you're an astronomer and you don't have access to the original provenance, you'll go to ADS and you will search for high redshift galaxy cold disk, and it will come up with a bunch of really interesting results. But it's difficult to then, you'll have to go paper by paper to see whether or not this is the object that they're talking about. So this is the sort of things that I was interested in solving. And this is one of this like ladder of problems where finding literature in a bunch of different contexts is extremely time consuming and difficult. It's a valuable skill to have for sure, but it also ends up taking a lot of time. For example, when I'm writing a proposal and I just need to find these papers before the deadline. So there's a bunch of different ways in which we go and find papers, right? We do things like keyword searches, or we're like, oh, I know that, you know, John works on these things, and so I'm going to go look up papers that he's on and hopefully find it that way. Or I go to conferences and I see people showing new results, and I'm like, okay, I'm going to write all of these papers down in a notebook that then I'll forget and never look at. But sometimes I'll remember and come back to them. Or there's online tools that use citation graphs to like link and find similar papers that get cited by the same people. What I want to talk about is how we can go beyond this and do something called semantic search. The core of semantic search is this. You try to encapsulate the meaning of a piece of text in a set of numbers, and then you have a search engine that just matches by cosine similarity, or how similar are the numbers for my query to the numbers of all of these papers, and what's the best matches. So this is where embedding spaces come in. So like large models like ChatGPT and so on tend to essentially learn embedding space after training and reinforcement, where when you give it a paper or a piece of text, they run it through the model and they produce a set of numbers. And what we call an embedding space is then when we do this for many papers, and then we organize all of those papers by some notion of similarity. So this is just a UMap showing a bunch of galaxy evolution papers that I was working with. So each point in here corresponds to a single publication, right? And then what you can do is you can ask it questions. It will go find the closest vectors in this space, and then it will use that as its sources in answering the question. So this is the basic pipeline that people found to mitigate hallucinations in LLM-generated answers and ground it in some source of information that they trust. The nice thing about the embedding space itself, beyond answering questions, is that it can be very interpretable, in the sense that you can see whether or not similar topics nest within each other. You can see whether, if you have a rough idea of what kind of papers lie in what part of the space, you can see whether the right telescopes are being used in the right, you know, set of observations. You can see whether or not different, like in this case, because this is about galaxy evolution, about whether or not different galactic neighborhoods, sort of how their publications relate to each other. And you can see whether or not observable phenomena like galaxy quenching, where they stop forming stars, and AGN feedback, which is thought to be one of the pathways through which this happens, sort of correlate with each other. They shouldn't be overlapping, but they should be linked. And so you see that like the two loci are, both of them are bimodal, and their two loci sort of like flip back and forth. Okay. So this was Anjali talked about what we did at JSOLT, and so we tried really hard to like take all of the knowledge that we had and what was state of the art at that time to take this RAG system and improve it and create this large corpus of data that Simone also mentioned, which now has close to 1 million papers. I think as of now it's sitting at like 960,000 papers or something, mainly from journals. And essentially create this pipeline where we do this similarity search as one of the steps, but we also do a few other fancy things like query expansion and re-ranking and filtering based on keywords and dates and citations to essentially find similar papers or relevant papers to any query and then answer questions based on that. So this was published in 2004, and it was a lot of fun to make, and a lot of people have told me that this has been useful in finding papers and keeping up with the literature. The user interface is super simple. It's just you go, like you can change a bunch of the settings, but by default you just go type in a question and you say run, and the sort of answer should have the provenance of what papers went into this, but also the actual thing that you're looking for. Claude also does this now. So does GPT, so does Gemini. So I don't regret any of the time that I spent making this, but you don't have to use Pathfinder if that's not of your preference. But it's really nice that this sort of like RAG setup for grounding answers in actual links or actual data is becoming more widespread. I think that's a really good thing. The nice thing that Pathfinder does differently from these is that it also shows you where in embedding space your question lies. So when you ask it that question, it's like, okay, that's where I pulled my papers from. And I'll come back to why that's important in a bit. But I just want to zoom in and show you, like, you get a first pass idea of whether or not you're actually pulling literature from the right area when you ask it a given question, because you know the topic that you're looking into. The galaxy evolution data set that I originally showed sort of lies there as part of my full embedding space now. So I'm just very happy with how we have grown it, and hopefully we can also start incorporating other fields into this at some point. So Pathfinder does a bunch of things like finding similar papers, answering questions based on those papers. It can also translate. So if you ask it a question in a different language, it'll reply in that language. And then you can use the embedding space to do a bunch more things. But the one thing I wanted to talk about in terms of reliability or trust, I think, is just, even when we do this, it mitigates the risk of hallucinations. It does not eliminate it, right? Because these are still generative models. They're making answers based on a probabilistic set of steps. And so what we wanted to do is also add an extra grounding step in Pathfinder. So this is work that we have been doing since it got published, where if you have a question that needs multi-paper synthesis, where it needs to like get its answers from a bunch of different papers and make statements, you can first see whether those papers make sense, especially if you know something about the topic. You can be like, oh yeah, these are roughly the, it's in the right ballpark of what papers it should use. And then you can take this, condense it into a set of atomic statements that basically, like, here's one statement from this that I'm assuming as fact to generate this answer. And then you can use these tools. So like this is one example with something called Lang extract, which is by Google, I think, where it can then go back and see what's the provenance of this statement given my source corpus. So you can go back and be like, any statement that it made, which paper and what part of it does the statement that it made come from. There's a few guiding principles behind Pathfinder. So one is that we wanted this to enable creativity and exploration, because the map of the embedding space is something that I've had a lot of fun showing at talks. We wanted it to lower barriers to how people do research and become comfortable browsing the literature, and we wanted it to be interpretable. We wanted people to know what the method is doing instead of it being a black box where it spits out an answer. And I'll come back to why these are important all the way at the end. But I want to now go and duck into like what we can actually do with just the embedding space. So leave Pathfinder aside for a bit. Just take that embedding space that we have and be like, how far can we push research using that? Oh, this should have been the previous section. So Pathfinder got used a bunch. It is close to crossing 200K users at this point, which I'm very happy about. I don't know why that was in this section. Sorry. Okay, so come back to the embedding space. The first thing you can do is you can group it by keywords and you can make it a heat map. And I then took this heat map and I pushed it through a diffusion model to make a very pretty version of this. I call this the prettiest plot I've ever made. And here you can actually like read this, because the mountains are the well-studied or the established areas where there's a ton of research on that topic, and as you sort of go down in elevation, you tend to be more sparsely populated, but still there's a bunch of papers there. When you start getting into shallow waters, those tend to be emerging topics that didn't have literature. So if you look at this as a function of time, it'll start out as mostly a bunch of islands, and then that becomes plains, and then that becomes mountains over time. So it really does promote exploration in a sense, because you can now go browse through this landscape and see how different papers have evolved over time, how they relate to each other. And you can do, I'm going to talk about 6 quick applications of what you can then do with this. So one is localizing UAT keywords. So you can plonk down UAT keywords and see whether or not they sort of span the space, or whether there's areas where they don't seem to fully cover. So like this one, I think, is like eclipsing binary dwarfs, which I don't know that there's a proper UAT keyword for that yet. You can look at the impacts of different observatories or different missions and see sort of like, are they having an impact in the cases where their original science documents said this is what we're going to do, or are they having unintended impact? So that's a very crowded plot. This is a slightly more, but not significantly better version of it, but showing 2 examples. So one where Kepler had impacts on astroseismology that wasn't in the original science scope, and Spitzer did a bunch of work characterizing exoplanet atmospheres that you can sort of see visually, that again wasn't part of, I think, its original mission. So that's 2. Third, you can find areas or topics that aren't either don't have up-to-date review or don't have one that at all. So this one is a map of the space colored with all the annual reviews articles plonked down on top, colored by year. So you can see the ones that only have, like, either have no reviews or only have red reviews are the ones that probably need an up-to-date annual review. We did a similar thing for reviews of modern physics, and so this is more physics, less astronomy. And so you can see that they tend to cluster mostly in the cosmology, dark matter region of the space, which makes sense. If you want to explore the space, you can go do it yourself. There's a QR code and this link, Explore Pathfinder, that lets you just like go browse around, click on different things, search for where your papers might lie, and so on. Number 4, you can look at how trends in research change over time. So we just took the default space and we ran a simple clustering algorithm to find like what the main clusters are. This is showing those clusters color-coded by age. So you can see that some of these are very old clusters, and then some of these are very new clusters. Yeah. And then you can sort of rank all of them by time and see, the dynamics of different clusters, both in terms of like their age spread, whether or not they have active research going on, and what they're about. And just because this is a galaxy, or because this is at ST, if you plot essentially the number of papers in a cluster versus the rate of new papers, you get a main sequence. Number 5, you can find areas for new research. So you can again do a similar density-based thing. So you can see where there are areas of low density in this landscape. So before this we were looking at the clusters. This is now looking at the voids, and look at essentially what papers are the closest to the location of of the center of the void. You can do this, and then you can start doing synthesis. So like, what are all of these papers about? So it turns out that particular void there is all about developing robust data-driven algorithms for working with transient or variable sources. And this was not something that we either had the data or the need to do up until recently. So this is very much an emerging cluster, and you can see that this is probably something people are aware of and working on and will get filled over time. Also, there's this very weird, interesting cross-disciplinary paper about how people are using source detection to identify cows. which is in my corpus for some reason, and I'm very happy for it. But another nearby cluster is looking at methods to make mock galaxy halo catalogs. And again, this makes sense given that we are going to have all of these really large survey programs and telescopes come up or are already in progress. So this matches the needs of the community and is another emerging cluster. So you can look at each cluster and you can be like, okay, so is this emerging? Is this dead? Is this lacking computational resources? Is this lacking observational resources? Like, what's going on? The last application I want to talk about is something that I've been working on the last few months and have been very excited about. So I'm resisting my urge to make the whole talk about this. But this is basically saying, we're doing all of this. We have a grounded system for searching papers, for sorting papers, and categorizing them in this landscape of embeddings. Can we now use this to write review articles? And can we make them cross-referenced in a way where they all link and talk to each other and get updated as new papers come out? So when I first pitched this to a few people, they were like, why do you want to do this? It feels like a lot of work. Will people use it? And will people think that it's not just AI slop? So I did spend some time thinking about it, and I came up with like this way of gauging whether or not I want to work on this. So you can take a bunch of different astronomy projects and you can put them on this heuristic of like, does the industry care? Are people in the industry going to work on this? Like, is Claude going to do what Pathfinder does in another 2 years? And is it going to help the astronomy community? And so I ideally wanted to pick something that is high on the astronomy priority list and not necessarily on the radar of what people in industry are thinking about. And the challenges are also like an interesting problem, right? Like, so you're dealing with extremely large data volumes that don't fit into the context windows of most models. You want it to be accuracy, you want it to be robust across, a range of different metrics, like Anjali was talking about. You also want it to have this impartial tone of, either an encyclopedia or something that not only tells you like, blah, here's like a list of results from papers, but more like, here's historical context, here's how this field evolved. And you want it to have living updates as new papers come out. And all of this is great, but the thing that I really am keen on is also having community input. So in making this so that you can actually put something out and people can comment and say, oh, that doesn't feel right, or that paper should have been included but isn't present, all of these things. So anyway, there's a bunch of challenges, and we ended up making something reasonably complicated but understandable. The TLDR is you start with the set of papers, you push it through and make these atomic snippets. Each snippet then gets routed to the correct page. Once a page object has like all the associated snippets of text, and like each snippet has provenance of like it came from this paper, it has this date when it was published, and so on. There's a writer that writes it, and then there's a critic that does a referee report. And and so after all of this, it finally gets built, put into a wiki, and then hosted on Cloudflare. Some interesting things that sort of are the intermediate steps of this are, one, when it's making the pages, it takes all of the snippets and it identifies thematic groups. So this is from a page on Barth-Tabor equilibrium models, and it's like, here's a statement, here's what it means, here's papers that support that statement, whether this has consensus, whether there are tensions, and what are the key results that came out in this topic. So it does this for each page multiple times. It also identifies consensus, where there's a claim that has either strong, moderate, or weak consensus, and papers that support it, or active debates where there's a question and there are multiple positions on it that both have supporting papers that say, oh, this happens or this happens, and all of this is folded into when the page actually gets written. So once it has all of this stuff, then it starts writing individual sections, right? Making sure that there's inline citations with the ADS bibcodes. It then goes through review where a bunch of agents check it for different things and say things like, oh, there's a citation gap, oh, there's a hallucination where you didn't, you didn't cite the number correctly, or there's a factual error where you reported something that doesn't make sense. And it, then does a referee report sort of schema where it responds to this and it fixes the things in the page, and then it does it again and it keeps iterating, ideally until it says clean and there's no more issues that it found. And all of that goes into this thing. So this is now live. You can go to lodestone.wiki and look at this yourself. It right now has close to 400 pages, drawing across over 100,000 papers. Mostly still centered on galaxy evolution because that's the thing I can actually find mistakes in, but hopefully will expand as we get more experts who can do the vetting process. So here's how a page, here's how a page looks, where you now have links to other pages. You have inline citations to papers. If you click that, it'll take you to the ADS page for that paper. And you have a table of contents on this side and an overall explorer on this side. I had to cap this at 3 iterations for now, just so that I could get this. I had something to show in time for this conference, which means that not all of the pages are converged. So you can actually see the referee's criticism that hasn't fully been fixed yet. So this is something that I wanted to keep so that I can show, like, here's the things that it picked out, and y'all can tell me whether this makes sense or whether it's too pedantic. And it also is like, oh, there's also like a few papers that I haven't fully incorporated into this text yet, either because I couldn't find like a good way to put them in, or because that information already exists. But again, as you iterate, it finds ways to put in even more papers. And there's a list of all the references that it used at the end of the page. The nice thing is there's also this like big connected graph that comes out naturally just from all the cross-links, the way Wikipedia has it. Right. And so it's also a nice way to then explore and go to different topics. So all of this was very fun to do, and I just want to end on a slightly sobering note about LLM ethics, because when we are doing this, there's an overriding set of concerns. So depending on which side of the internet bubble you live in, you could either think AI is the greatest thing ever, or AI is the worst thing ever and out to make all of our lives irredeemably bad. And AI development also is a minefield. Like, while I'm doing all of this and it's all very interesting, there's also a bunch of ethical and technical concerns that I need to be aware of. And I think everyone should put some time into thinking about these things as we make all of these apps and, do all the cool stuff that we like doing. So I want to come back to that set of development principles for Pathfinder and say that if you are making an AI product, these are some things to think about. Like, make sure that you're trying to do something that is enabling people to be more creative, and like actually removing something that's a barrier for getting to the science, whatever that might be. And that things are interpretable, that you're making things that genuinely like have some scale of knowing what the model does. And astronomy, again, as I don't need to say this to most of the people in this room, tends to be a really good AI safety sandbox. Like, I like developing things and tools for astronomers because we are a very unique combination of being both engaged and critical, right? Like, so we try things, but we are also very skeptical, and we're like, we need to do better at this. And Sanjeev was talking about the well-defined ground truths. I think this makes a lot of sense. And overall, as citizens, as astronomers, I think we just need to be informed, be transparent, and demand transparency, and push for some regulation in terms of how all of these models are built and developed. So I'm going to leave my summary up here, and thank you for giving me this chance to come back.
Right, so thank you very much for this awesome talk. And since there's a lot of content, I think there might be questions. I don't know who was first, but perhaps we will go with you, Anton.
Sure, yeah, lots of fascinating stuff here. I just want to ask something about the wiki idea. So like,
and don't take this the wrong way, it sounds like a sort of 2015 solution to a 2025 problem, in the sense that, one of the things people use LLMs for is to ask very specific, and one of the things Pathfinder is really interesting about is you can ask like a specific question, and it gets regenerated every time, right? And that's sort of the value of it. So can you just talk a little bit about why you would want to do a wiki format, which is sort of more like not as specific? What do we gain from that versus just asking the LLM in the first place?
Yeah.
Summarize this field for me.
Right. I think this came out of work that I've been doing with undergrads, and the thing I wanted them to sort of get is an idea of how to explore rather than just ask a targeted question and get a targeted answer. And the second half of this is when the shelf life of a review article tends to be growing shorter as the progress of scientific growth accelerates and we put out more papers all the time. So what I wanted to do is combine those two things and create something that sort of has the qualities of a review page, but also it's a living document. It gets updated as new papers come out. And so it stays current to some extent. And then it becomes a thing that like a grad student or an undergrad student, or even me when I'm writing a proposal and just need to know state of the art in a given topic, can go read the page. And yeah, like I still go back to Wikipedia for a bunch of things. So I think I wanted to do something like that, but with papers.
Yeah, it looks like you have a follow-up question.
Thanks, Karthik. This is really. Can you say a few words about how you or the system relate to the island map? Consider papers that are obsolete, so results that have been now, they become old and not more accurate, but also papers that are clearly wrong gets a lot of citations, right?
Yeah.
So can you say a few words about how these two problems get folded into this? The paper, the new science that contradict old science and therefore is now the new norm.
Right.
Something that's really, really wrong.
Yeah. I think we try to explicitly design for these things in the back end of this. So just going back to this. So when we do this, like when it does the thematic groups, it still finds groupings in literature that tend to like subscribe to a certain viewpoint. And that makes it straightforward to then look for consensus and lack thereof when there's, multiple possible reasons that could explain like an observation or something. And we just try to highlight that even when the article is being written. There's also something called, I don't know if I'm showing it here. We also track something called paradigm shifts, where it's like, oh, this method used to be used and then it got, or this assumption was very common in the community and then it got superseded by literature at some point. And then every time a paradigm shift happens, those papers get shifted from the main sections of the wiki page into the historical context section. So it then like says this is what used to happen in the community, and then the main pages tend to have current results.
Right, I think we have time for one more question. I think you were next.
I'm a huge fan, excellent work. So quick question and a follow-up. Which models are you using? Which language models?
Oh, so this is all thanks to Joe, who got a very generous grant of about 10K Gemini credits. So that's what I'm using. So this is all a combination of 2.5 Flash, 3 Flash, and 3.1 Pro.
Great. I was wondering if you've tried comparing quality, if you dump a bunch of papers in a notebook LM and like how that compares. You could imagine you have this wiki, a new paper comes out, you could ask one of the big models to ingest a new model or a new paper into the wiki. Compared to all of this infrastructure you've built. I wonder.
No, absolutely. I think that's something we can do in one of the hacks here and see what it does. Yeah. Thank you.
Awesome. So let's thank Karthik again.
Thank you very much.
Up is Vicente Amado, I believe.
I'm sorry, which one was it? The Olivo update. Okay, that one. And we can put it in. Oh, and you need one of these. I guess just for the online paper. Yeah, exactly. Well, just for the recording as well. And you gotta turn that on.
You can put it anywhere.
Yeah, just somewhere. Okay. This is the
Okay, perfect. Hi, everyone. So yeah, my name's Vicente Montolivo. I'm a PhD student at Michigan State University, and I'm excited to share this paper, which we're working on in collaboration with ESO, and specifically Teresa, on benchmarking representation methods for expertise of reviewers in peer review. And so as you can see, the number of proposals, of observing proposals submitted to observatories is growing, and it has strained the peer review community. Many people working on these different things across observatories have identified many challenges with the growing number of proposals. I just chose a few of the large observatories, but and if you look at GWST, just in their first cycle, they received roughly 1,100 proposals, and then this last cycle received 2,900 proposals. So it's growing a lot, and this is causing some challenges. And so this motivated observatories to identify different solutions to alleviate these challenges. And one of these challenges is really driven by the legacy nature of how we do science, the manual processes of how we do science. And one of these is manually matching reviewers to proposals by distributing proposals and reviewers to panels across topics. And so this scaling to thousands of proposals makes these manual efforts a bit unsustainable, and so a majority of observatories have started to adopt automated methods to identify relevant experts for individual proposals, specific proposals. And the basic way that this is done in astronomy, but also across large computer science conferences, is by computing the similarity between some sort of representation of your proposal text. That can be just of the abstract of the proposal or the full text, and some representation for the reviewer. And there are various ways that this is done across fields. And currently, each observatory uses a different method, and other fields also use different methods. And so these have been adopted, and some of the different ways that this is done is using different input data. Some methods use maybe just self-reported keywords, might use your previous proposals you've submitted, or the publication your publication history, so abstracts, etc. And they also utilize different methods for that representation, for that vector representation. They might use more statistical-based methods, leveraging word frequencies, or some are now advancing to using neural network-based kind of embedding methods, kind of like Karthik was describing, these embedding methods. And so our goal, in collaboration with ESO and Teresa, is to benchmark these expertise modeling methods to really understand how they perform and how the methods align with the goals of peer review, such as reproducibility, transparency, and really, are we identifying reviewers, or expert reviewers. And so to do this, to benchmark these various representation methods, we leverage the distributed peer review framework. And just as a reminder for anyone who doesn't know what that is, it's basically one of the submitting authors on the proposal must then serve as a reviewer. This is similarly done across large computer science conferences where you submit a paper and then you act, one of the authors on that paper must act as a reviewer. And so we use the initial implementation of distributed peer review, DPR, at ESO, which was in 2022, and that gave us roughly 435 proposals, and there were 379 unique reviewers nominated. Some were on multiple proposals. And so then, for each proposal, for a single proposal and a single reviewer, we can then calculate the similarity between them under some sort of vector representation. And then that gives us some pairwise similarity. We have a matrix of similarity scores, between 0 and usually 1, but the method that I use for this one doesn't matter really. But you can kind of have this comparison of all the different similarities between your proposals and reviewers, and then you can identify which reviewers you should use for a specific proposal. And here on the diagonal, for our similarity matrix, that signifies the similarity between the proposal and the proposing author, so the unique reviewer that, or the reviewers that were nominated. We sort it that way so that we can track them. And so we do this for all the methods that we benchmark, and we benchmark 6 based on the different methods used at different observatories and different computer science conferences. And some are more statistical methods, and some leverage embeddings. And if you just look at the raw similarity scores, you can't really just compare them and say, you know, maybe the keywords method or these embedding-based methods do better because they have more similarity. Those aren't reliable evaluations, so you have to define some standard way to compare the similarity scores across these different methods. And we formulate the task as an information retrieval problem and really leverage the distributed peer review framework. This enables a comparison across the performance for each model, and when we treat the proposing author as an expert for their own proposal. So we use that as a label, a proxy ground truth that allows us to then see how well these models retrieve some sort of expertise. And so for each proposal, we have what in information retrieval is called a query, and then we can compare them to all the documents. And similarly, as we did before, we have the representation methods, and those give us scores. And so now we have a ranked list. These are just some random names of my friends that I put on there with scores, and we can rank them and see where does that labeled reviewer that we know is an expert, where do they rank? And we can use information retrieval metrics to then evaluate how the different methods rank the author of their own proposal. And so across our different methods here, we plot the distribution of the rank of the proposing author in the list of possible reviewers. And various methods do perform pretty well, but TF-IDF retrieves the proposing reviewer as a top expert higher on each ranked list across all proposals in our data set. And then similarly across various metrics, TF-IDF, which is a statistical-based method, really leverages word frequencies, has the highest metrics. And specifically, I think this is a pretty informative metric, which measures whether the relevant item, which in our case is the labeled expert, appears anywhere within the top 25 results returned by the model. And TF-IDF retrieves the proposing author within the top 25 experts, 79% of our proposals, compared to some of the embedding-based methods are a little bit lower. And so, in this specific retrieval task, this statistical-based representations currently outperform the retrieval of experts. Possibly strict vocabulary matching on specific subfields does help TF-IDF and takes away some of the noise that maybe the semantics of the proposal or of a reviewer's papers might include. We're still kind of thinking about this, and distributed peer review really enabled a good evaluation of this. And so, yeah, thanks for listening, and you can follow our work here and check out the paper when it comes out.
Awesome. Thanks a lot, Vicente. I think you were first.
That's interesting. So the problem that there's a bias in all this analysis, because everybody starts from either the list of names you already have as a reviewer or scientist, or the list of people that proposes. Right? One of the things that we need to do also is democratize science in a way that we expand the list of reviewers. So finding the members of the communities plural, that can be a reviewer even though they never proposed. Mm-hmm. And so that's the part that's still missing here. You have difficulty to find reviewers because your list is fixed to begin with, or it's very slow to expand.
Yeah, that's for sure a big problem, and that is, for our research group, is a big question that we've been trying to solve. Some other work I was going to present together with this is a challenge that we've been trying to solve called author name disambiguation. So if anyone wants to talk to me about it after, I just didn't think I could talk about 2 papers in 8 minutes. And so, our goal is eventually to basically create researcher profiles so that we can then find any expert worldwide. That does take some working with different, the observatories to, adopt this. Some observatories are still interested in just a panel-based system or this distributed peer review. But yeah, our goal is to have, an open source, way for you to find any expert worldwide for, paper, proposal, grant, etc., so that we have, we can leverage everyone, so it's fully distributed instead of just relying on whoever proposed.
Okay, and I think we have time for a quick question, maybe.
Yeah, this is really neat stuff. But I'm curious about one element that you may or may not have thought more about. Capturing expertise just through the proposal is very imperfect. I know a lot of things that I've never written down, and the old way of personal networks captures some of that and not all of it. So do you have any thoughts on how to grab that information that's not written down in proposals but is still really important for understanding someone's expertise?
Yeah, I haven't fully thought about that, tacit knowledge. We try to leverage whatever data we do have, so easily accessible papers, through the NASA ADS API. We request 25 papers in the last 5 years. We use your previous papers, but if it's not data that I have accessible, that does make it hard. I know computer science conferences do allow you to upload whatever papers you do want. So maybe you were on a paper that you're not fully an expert on, so you could actually just decide what you're confident in. You could possibly add other notes or different things. Like you could kind of create your own profile, and we could use the language to find the similarity between those two things. But I know in computer science people try to game the system so that their friends review their work. So if you create your own profile, it might be easier to game the system. It's not as big of a problem in other fields, but yeah.
Right. Thanks again, Vicente.
Thank you.
For the next talk, we have Amber. And I realized I mixed up the sequence of talks earlier, but that was just a test to see who memorized the agenda. Bye.
Oh, it's huge. That's great. Hello, I'm Amber Malpass. I work at the Ohio State University. Most of my work these days is with the Argus Pit, and we are preparing for Roman's launch. I don't know if you know, but Roman is launching in September, and we are expecting on the order of tens of thousands of microlensing events, thousands of microlensing exoplanet events, and hundreds of thousands of transiting events.
Very hard to hear you.
Sorry, I'm quiet. I'll stand closer. I'm going to tell you about all the times I face planted trying to make a rag bot. Oh, cool, thank you. So why did I want to make a rag bot? Like I said, we've got a lot of events coming, an amount of events that are similar to how many events we've analyzed as a community over the last 30 years. So we've done a lot of work to make automated pipelines, but at the end of the day, we just need a larger workforce. So we are doing a lot of things like improving our learning resources and other things to try and make the field more enticing and encourage people over. One of the things we're doing is creating a data challenge, which I am helping to organize. And we have challenges in that everybody has too many jobs. So we really want to help people and make sure this is a frictionless data challenge for them, but we are not always available, and we don't know all of the details about how very specific microlensing codes work. So I wanted to create this RAG bot to help participants so that they could find like really accurate, up-to-date information specifically about open source codes, APIs, things like that. Verifiable so that they can go and check on the repos and get what they need. Easy to use, easy to access, and saves a lot of interaction for us and people being too scared to ask questions. So the first thing I'm going to tell you about is my phase 1, accidental agent. So the first thing I did was grab some code for a Slack bot and TextAI, which does embeddings and creates like RAG databases for you that you can index, smash those together, RAG bot. Great, lovely. The issue, the RAG's not good. So we've heard a lot about RAG today, but we've heard a lot about people doing RAG on academic papers. I'm not doing RAG on academic papers. I have a couple, but mostly I'm doing RAG on code bases, and it's a little bit different. And generally these embedding models are struggling. So my solution at first, because I was just like, I don't know how to deal with this, was thinking about another bot I'd created, Gilmore, who was for my D&D group. He's a shopkeep, and he tells us how much stuff costs. He's flamboyant and lovely, but I thought it would be really great if he could do actions like respond to our Discord messages with sparkles. So I gave him spells, and in his system prompt, I told him if he used specific strings, I would regex out the bit in the middle, and I would respond on Discord for him. I accidentally created MCP tools, but they already existed, like not created. So I did this to Nancy as well. I thought, okay, her RAG's not good, but the knowledge base is there. So instead I will give her tools. If that did not line up well, I'm sorry. I'll give her tools. I'll let her SQL search the database. I will let her retrieve specific files. I will let her look at the document tree. I will let her reweight rubbish files so that they stop coming up in RAG. And I will let her choose when to respond so that she can think about how to use her tools. The RAG is still rubbish. So phase 2 was to try and figure this out, and now that I've realized MCP exists, I ripped out her guts and refactored this into 2 packages. There's a Slack bot and an MCP server. So the Slack bot is the head here. This is what interacts with people. Then you've got the MCP server. This is with her tools. And then all of that interacts with the pre-embedded knowledge base. Right? The benefit of this is that this is really easy to share and reuse in different contexts. So we can rip off the Slack bot head and replace it with a VS Code coding agent or Claude Code, or hook it up into a custom GPT, and all of a sudden ChatGPT in your normal browser window has all of the knowledge about my data challenge that I want it to know. This is free to use for everyone for infinity as well, which is great for me because then I don't have to pay for all the API calls with the Slack bot. The issue is the RAG is still rubbish. Okay, so now we need to fix this problem, but at least we've isolated it. So I'm going to try some things out. This is my knowledge base. It's full of articles, repos. The repos are full of lots of different types of files. I chunk by file, I embed it using TextAI, and I try and get cosine similar results to my queries. It's not going well. So first thing I try is just experiments with code embedding specifically to see if that helps. Honestly, it's not helpful. I try a bunch of different things. I spend a lot of time down a rabbit hole that goes nowhere. Okay, fine. The next thing I try is the reweighting was working quite well actually. So why don't I just send the whole database through an AI and get it to give weights to each file about how relevant it might be for the data challenge or someone trying to code. That way I can get rid of like init files with nothing in them and stuff like that. It still sucks though. So the next thing I try is I rip out the part that chunks things and I create a chunking package and I use a sliding window chunker. Why? Because it was easy. It's better. So this is promising, but it still sucks. So the next thing I do is I create AI summaries. These are text representations of what the whole file does. This helps with the embeddings because it gives like semantic context that isn't always there just from the code alone. This dramatically improves the RAG, but it still is mid. So the next thing I did was change my chunking strategy again into something that was a little less blind chunking and a little more thoughtful. I start chunking on concrete context trees. concrete syntax trees, cells and sections and notebooks and sections and paragraphs and text, and now all of a sudden the context that was being spread over a whole file is specific to these small chunks, and the cosine search is more able to find pieces of documents that mean certain things that match my queries. It's looking good. Okay, well, it's not great, but it's looking better. So basically, I think my issue comes down to one really key fact, which is that when an embedding model embeds this monstrosity of tokens, it's really not that similar to the word's distance modulus. So in theory, the coding model should handle this, but it depends on their pooling strategies, which I now know about. And it depends on how they've been trained. And so I think at this point, the next step is to go back to the embedding model and take another look and see if I can improve that, but also try to sanitize the inputs a little bit. So phase 4, Nancy is actually good. I have been kind of bagging on her here, but with her tools, she's a great bot. She's a really helpful agent, and her tools are really helpful with VS Code if you're trying to solve analysis problems. So I have been trying to make all of this work more worthwhile by creating a reusable Nancy brain. So this is a thing where you can instead load your own dependencies for a project from a YAML requirements or PyProject TOML, and now you have a database that your agent can search through to help understand packages that you're using when you're coding. Specific versions of packages, which can always be an issue, especially in microlensing where they love to change the API. Then you can upload BibTeX files or ADS things. That's great. The next thing I'm looking at doing is ripping out my PDF processor, which is a little bit temperamental and average, and swapping it out for DSMO. Hopefully that'll fix some of the issues I'm having with articles. But in general, now Nancy becomes something that you can clone and use in your own builds. And the plus side of that is you can use her over STDIO, and she's nice and safe, and you don't share your data anywhere. But if you do want to do microlensing, you can connect to my hosted Nancy brain. You just need to curl with that command there to get an API key. And then you can hook her up without having to have any code on your computer, just the settings file. I really hope that's right. The agent created the settings file, so let me know if that's wrong. Or you can clone the repo or pip install Nancy Brain and work through building your own server for yourself. If you decide that the RAG is rubbish and want to help, I would love contributors. But I'd like to give special thanks to Dob Debonaire's Slack machine and TextAI, TreeSitter, and in the future, DeepSeek-OCI. If you want to join our Slack channel and play with Nancy, that's the code. If you want to play with the GPT, that's, the QR code, you can use that too. If you're still on my Slack channel for the data challenge in like a week and you're not signed up, I will kick you off. Please don't take offense. Okay.
Right. Time for one question, please.
At different stages when you decided she was rubbish or not so great or good enough, what were some of your criteria in your mind or else explicitly stated?
Right, so I should say that I am extremely familiar with the knowledge base I gave her. And so my criteria for rubbish was relevance. So if I gave her a query and I knew that there should be an answer for it and I did not see anything near that answer in the top 10 results, I think, well, that's not great. But it is really qualitative. So that was definitely made exploring good options really difficult because you don't have a good metric of did this help or did this hinder if the results are just bad. When things started to look better, it got a little bit easier. But when they were bad, it was just searching in the dark, really. I did also... Part of the benefit of ripping out the MCP was that I could hook up a UI to it so that I didn't have to interact with a Slack bot just to see if its RAG was good. I could just use RAG on a little website and see what the results were that were coming back, and that helped a lot.
Right, let's thank Amber again. And next up is Attila.
Okay.
Thank you very much. Can you hear me? I think so. Okay. So good morning, everyone. I'm Attila Alkan, a postdoctoral researcher at the Harvard-Smithsonian Center for Astrophysics. I'm very happy to be here because I missed the first edition in 2024. At that time, I was writing my PhD manuscript, and so it was like almost a near-death experience. But it's okay. I did it, and I'm here today. So today I will talk about a topic which sits right at the intersection between natural language processing and astrophysics. So we address the problem of automatically assigning scientific concept to a research paper at a larger scale. So I'll walk you through our motivation, the corpus we built, AstroConcept, the experimental setup, and the experiment we conducted, our results, and I will conclude with some takeaways and open questions. So why multi-label classification in astrophysics? Why does this matter? So the volume of astrophysics papers is growing faster than any team of human curators can handle. So at NASA ADS, the Astrophysics Data System, we index hundreds of thousands of papers, and for a researcher to find what they need, the papers need to be tagged with controlled vocabulary. And controlled vocabulary is very important, so no free text, no free keywords, but keyword concept that comes from a standardized vocabulary. So in astrophysics, such controlled vocabulary is the UAT, the Unified Astronomy Thesaurus, which contains more than 2,000 concepts organized across 11 hierarchical levels. Assigning this concept manually is expensive and doesn't scale, so the question is, can we try to automate this process? And the challenge that we have here is the label distribution, is that the fact that the label distribution follows a power law with an exponent of 1.5, as you can see on the screen. So what does that mean? In practice, it means that 76% of the UAT concept have fewer than 50 training examples. So this is not a standard multi-label classification problem, but this is an extreme multi-label problem in a long-tail regime where most methods simply break down. So in order to study this multi-labeling problem, we did a benchmark with our team. We tried to look at the existing corpora in the literature, and we found a gap. So as you can see on that table, existing data sets are either too broad, so they will cover like a multidisciplinary science corpora, or they use shallow label hierarchies, and they don't necessarily use always controlled vocabularies. So we found that none of them really combine a tractable scale, a deep hierarchy, and a domain-specific vocabulary at the same time, and none of them cover the astrophysics domain. So that's why we tried to fill this gap by proposing our corpus, AstroConcepts. So AstroConcept is a corpus that we build. It composed of 20,000 English abstracts that we extracted from the NASA STScI. It was not difficult for us to extract these. These papers cover a temporal period from 2018 to 2023, and we select the main selection criteria to collect these papers were that we get papers that were submitted at the Astrophysical Journal, maybe because these journals require that the authors assign keywords coming from the UAT taxonomy. So at least we are sure that the labels, the keywords that we are dealing with are coming from a controlled taxonomy. So as you can see on the table, so we have approximately the corpus has 93,000 of total label assignment, with an average of about 4 labels per paper, per abstract, and we observe like 1,800 unique concepts that's represent 92% of the full UAT taxonomy, which is a good coverage. So as I was saying, the imbalance is severe. the most frequent label, I give here the example of galaxy evolution, occurs like over 1,000 documents, and with a median label appears in only like 12 documents. So to make this imbalance more concrete, we split the label space we have into 3 frequency bins. The head labels, these are labels that appear more than 500 times, which represent less than 1% of unique labels, but 13% of all the assignment. The torso labels that occur between 50 and 500 times cover 23% of labels and 67% of assignments, and the tail labels, the labels that are the most rare, so which have less than 50 occurrences, cover 76% of labels, but only 20% of assignments. So this is the core challenge here we have. Most labels are rare, and that's exactly where the systems usually tend to fail. For our experiment, so the input data was the title plus the abstract, and here the task is to predict the correct subset of UAT concept. We split our training set with the following ratio, 85 and 15 for the test set. For the evaluation purpose, we used common metrics for multi-labeling task, precision recall and F1 score, and the results at different levels of K. So I'll show you here our main pipeline. So the main pipeline is a 2-stage pipeline. So first we fine-tune an AstroBERT model that retrieves the 50 candidates and given an abstract. Why 50 candidates? Because it covers 82% of recall. And then we ask DeepSeek, the language model, to filter among these 50 candidates and give us the final label. So this way, the LLM never generates free-form concept, but it only selects from AstroBERT's constrained candidate set. So we reduce the hallucination problem or the invalid UAT terms. So as we can see, the overall results, so DeepSeek performs better. In our benchmark, we compared like rule-based method and supervised learning-based methods, and DeepSeek outperforms in terms of F1 score. So this vocabulary constraint performs even domain-specific language models like AstroBERT, and it doesn't need any fine-tuning. It was only the inference. We also measured the difference, the drop into the performances between the head labels and the tail labels, and we can see that DeepSeek is always better than AstroBERT and any other language models. So here to summarize, which paradigm handles extreme imbalance best? So it's the vocabulary constrained LLMs. It shows 3% better head-tail balance than supervised approach. The second question that we're wondering, does domain adaptation benefit all frequency equally? No, the gains concentrate on rare specialized terminology, and the head concept improve only modestly. And last point, can vocabulary constrained LLMs compete with domain adapted models? We have seen on the results table that yes, the hybrid pipeline surpass AstroBERT by 16% of F1 score at the inference cost only. Thank you very much. If you have any questions.
Thank you. And we have time for one question. Please.
Yeah, as an alternative for, so when you're using the large language model and you are feeding in the AstroBERT, top 50, that still might not be, like, you're cutting it off at 82% recall.
Yeah.
But you're also giving it this crutch in the form of AstroBERT. Have you considered something like asking the LLM to generate the maybe top K categories as descriptions, and then embedding those and matching those embeddings to the categories in the UAT?
Yeah, that's an interesting aspect, and the reason why we provided like a list of 50 candidates, it was to reduce the hallucination, because if we give the freedom to the LLM to generate keywords, most of the time these keywords it's difficult to map them with the UAT taxonomy, or at least I didn't really try that, but from the experiments I conducted, I was seeing that a lot of time it was providing keywords that were not in the UAT taxonomy, so that mapping was difficult. That's why we provided a list of 50 candidates. And why 50? It's because there was a recall of 82%. And here there was a trade-off between, okay, it would be better if we can give the full list of UAT concepts, but then the hallucination increases. So it was a trade-off to find. And some other complementary experimentation are still in process, and I will continue to explore more. Yeah.
All right. Thank you. Let's thank Attila again.
Thank you very much.
Next up is Ashish Mahal.
Good afternoon. My name is Ashish Mahabal. I'm from Caltech. I'm the Deputy Director for the Center for Data-Driven Discovery. And today I'll be representing a large team from Armenia, and people are mentioned down there. So Narek Saakyan is the PI of this project. This is Astrogenesis. We have been hearing a lot over the last 2 days, yesterday and today. There were some great tutorials yesterday, very good talks today as well. And so we've been seeing how the large language models have been improving incessantly, and there are so many models that are getting bigger and generalized. But what I'm going to also say is that there is also a good area where it is important for us to have very specialized astronomy-related agents also, and Astrogenesis is one of those. And I'll mention a little bit why that is important. So right now it is only for blazars that we have, but it's going to be generalized for more specific astrophysical domains. In particular, what we have is that there can be domain-specific research modules that can be added. So what you see here is that this is the general way things would work. So you have, as in LLMs, you've got a user, there is a query response and so on, and through the DSRM, what can be done is that it can be going to different individual agents that are there. So the important things here, which are different from a generalized LLM, are that when you have these expert curated models, they can be more physically informed. The science grade validation can exist with that. There are neural networks at the back end. So when you're posing a query, it is not just the what is the next word, what is the next word, what is the next word that's coming in. Even if there is reasoning in LLMs, you have largely that here. Actual neural networks can be run in the background. Models can be run with the specific queries that you have, and the answers will be based on that. And then there will be full citation and reproducible pipelines. So again, there is the whole literature that is properly indexed and so on, and the interface is user-friendly. So this is the broad outline of how things look there. And there are 4 primary agents. One is the literature analysis, existing papers from arXiv and from ADS, which are properly indexed. There are vector databases, a separate database for the papers and a separate database for primarily the abstracts and authors, etc. Data retrieval, again, there is a set of databases which are well curated. You can also provide your own data, and so it can come in from there. But these 2 are the main ones that are somewhat different. So you have got physical modeling, and that's what I was mentioning about neural networks. So you can have questions that are put specific questions where you want a specific model to be run, and that can be run, and you can get answers related to that. And the way this will be done is that there will also be a set of memory that exists, so that a lot of models don't have to be rerun again and again. So there'll be a little bit that can be taken from there. And research ideation. So a question was asked earlier, for instance, if there are questions, there are theories that are opposing each other, what happens? Meaning if there are papers with theory A and papers with theory B, how does that come out? So this agent, what it will do is that it will give you back information from both of them, and you can decide where to go next, what happens itself. And so the supervisor agent is the main agent through which you interact, and it will go to these agents by itself. We have heard various terms like how to go back and forth between the turns. So there is no fixed number of turns as of now. And so the supervisor will go fetch answers coordinate with that. And if it's a simple question, the supervisor will directly try to answer that. And then what will happen is that it will go back and forth. There'll be multiple things. Each of those agents also have sub-agents. You may not have access to them directly as of now, but that's something that we are considering whether that should be given. For instance, there can be a flaring sub-agent where what happens is that when you have the physical modeling, it would go back to that and check for flares and things like that. So again, the same kind of things that you have in LLMs in agentic, but these agents are somewhat specific to the kind of astrophysics that we'd like to do. And there's some additional detail of these things, so we don't have to go into this text. The slides will be there. You can take a look later, the literature agent and the data retrieval agent and the physical modeling agent and the research ideation agent. So this is, again, a key element of the whole theoretical modeling agent. What is it that we are trying to get out of that? So the thing to remember is that we don't want to replace the physics, right? Meaning we have neural surrogates, and that's the kind of thing that we have, but that's not going to replace the physics. The physics still takes the main stand there. And it's the repeated model evaluation that can be replaced with that. And so what you see is that there are many bottlenecks that exist, and what we are trying to do is that trying to use these methods to go around the questions that exist, go around the problems that exist, and make sure that these are very well-grounded answers that we can come back with. And this is how the interface will typically look, and you can have questions like model the attached data with hadronic model. This right now doesn't exist in LLMs, for instance. It may not have enough deep knowledge for that. The redshift is such and such, consider EBL absorption true and assume 1 neutrino in 1 year and so on. And then you can refine that as you go along. So this is the kind of thing that we should be able to answer quite easily. And those are the kinds of details that we can go into for Blazars right now. And that's what we want to extend to other areas also. So this is where we are right now, Blazar focused neuromodeling. There's raw data pipeline integration going on, and this is really the future where we want to go. So expand it to GRBs, expand it to TDs, expand it to full astrophysical operating infrastructure. But again, it won't be a general astrophysical thing. That is, when you go in, it's not a single model that's trying to give you answers to your question, but it will go to sub-agents that are very specific to the areas that you want to. And this we are hoping to release by the end of the month. It's already there. We are just prepping up the main web page, and we are open for collaboration. So if any of you are interested in doing that, we'd be happy to do that. So one thing that I would like to mention before I finish is that just a few weeks back, there was a big AI summit in India where Denis Hassabis and Jan LeCun and Joshua Bengio, etc. were there. So there were some interesting controversial talks that happened there, how these experts oppose each other in some way. So the world is talking about AGI. We are going towards artificial general intelligence, but at the same time there are opposing views where what will happen is that there cannot be a single entity that will know everything about everything. And so that is where you need these specialized models. That is where you need these world models. We also need to be very careful about the ethics and what kind of data that we are picking and so on. So those are the kinds of things that are going into some of these, and we hope to keep on developing on those lines. And again, as I said, we're open for collaborations to take it to more areas of astrophysics and so on. And I think I'll stop with that and take a few questions if there are any. Thank you.
Thank you, Ashish. I think you had the first question.
Sure. Yeah, thanks for this. It's really interesting. Just thinking about the users first, right? Like in terms of like if astronomers are seeking to build understanding, a critical part of that is like inspecting, where things either, within this, massive reasoning chain or agentic workflow, like things could be going wrong, or at least building up the trust and the validation for that. But as these kind of workflows become more complex, then of course it gets buried in that. So do you have a good framework for thinking about how do users evaluate as we sort of, as these agent operations get more complex?
Right. So I think so long as you keep it tight, this is primarily a RAG framework. So we have got these literature, we have got these papers, and what it's going to look at is whether it gets text that is directly connected with that. So it should be confident enough to say, okay, I don't think I have an answer in what I have to give it to you. So try to avoid any hallucinations in that way. And if there are, as I said, if there are things that are opposing each other, be able to present both of those. I think that is a good element for trust and not having hallucinations. But you're right that if right now we have got 80,000 papers related to blazars, but if it goes to say 1 million or so on, there'll be more varied things. And so we'll want to come up with things that can show that in a nuanced way as well. So it is a complex question, but I think just by sticking to databases, data, and papers, we can try to ensure that we stay away from hallucinations and other things related to that.
Yes, please.
On your query, you told the chat to assume a few things, 1 neutrino per something.
Right.
If you don't tell it to assume something, does it assume something a priori, or do you tell it some basic knowledge to assume?
Yeah, good question. So it depends. Depending on the query, either it'll do something simple and tell you what it has done and give you the other options as these are the things that could be changed. Or if it is too complex or too open, then it'll tell you, can you specify more things about this and this? That is what I would like to know, and then it'll proceed with that. And that is why if you know the exact question, it's sometimes good to do, but that's why this is a very specialized model, and if you go and ask a very general question, how many blazars are there in the universe? So it may dilly-dally a little bit saying that I'm not sure how to answer that. It may say that going to this database, I have so many, but is that what you're asking, for instance, like things like that.
It does have some memory.
Yes, it does have some memory, but that is something that the user should be able to configure in some way. And that's something that one of the earlier talks that was there, where they're trying to see what different questions users are asking and so on. Based on that, these systems can be improved further.
Yes, you were first, I think. Yes.
Very interesting talk. I was wondering if you could explain a little bit how you made the network physically informed, and if there was any like safeguards to make sure that the user couldn't mess with the physically informed at all, to make sure that they didn't mess with the physics going into the network at all.
Right. So that is a hard thing to do, right? Meaning if they say, for instance, that don't assume 1 neutrino, but let's say there are 1 million neutrinos coming or something else, right? Meaning the network in principle can try to evaluate that. And that is, I think the onus of that part is on the user, but it will be tied to the question that was asked. And what has been done about the guardrails is that a lot of standard things that astrophysicists use in blazar science and so on, those have gone in. Again, what are the papers that have gone in? So one of the questions, again, in earlier talks is that, can you reproduce some of the computation from the papers that are there? So those are the things that have been used to put that in. But again, that is an area where definitely more guardrails can be put in to see that. I don't know if it is worth telling a user that, no, you cannot have 0.3 neutrinos per year, or you cannot have 3 billion. I don't know. That's something that we'll have to understand from the community how that should go.
Right. And I think we have to progress now to the poster talk.
Thank you.
So let's talk,
Briefly, yeah.
briefly.
So the next thing that we're going to do is we've got, I believe, 4 poster pops, 2 minutes each. If you are one of the poster pops for this session, please come line up over here. And just for everyone else in the room, these posters will be on display during the afternoon coffee break. Everyone gets lunch free from having to present a poster. So these are a little bit in advance. And when the poster pops finish up, I will give a few logistical comments.
Okay, I'll just go.
That was the first one. But that's fine. Yeah.
Yes, time is
up. That's fine.
The order is fine.
Yeah. Just talk to those microphones.
All right. So this project is a little bit different. It's the overview, or what we were thinking about in this project was thinking about kind of far future space missions and how we kind of maybe even do autonomous, introduce autonomy, especially with onboard processing. And so we focused on the idea that learning is compression. And so we decided to retrain a small LLM to compress astrophysical data, namely exoplanet data that we had. And so we wanted to kind of explore the spectrum of different types of data
in different stages, but for this project, we focused at the lowest level, just the raw data, and we had some success in actually making a lossless compression algorithm for exoplanet transit data. So you can see that in the poster if you come talk to me, but we also note future extensions that kind of go more towards multimodal, like multi-instrument, different types of targets, not just exoplanets, could be galaxies, or even different types of labeling for trying to figure out how you best represent the data that's on board, maybe by introducing some lossiness to it.
All right, hello, I'm David Rodriguez. I work at MAST, and we've been hearing a lot about MCPs, Model Context Protocols, right? This is a tool you can use to essentially expose external resources to an AI agent. So I figured, why not do this for the MAST archive, right? The Mikulski Archive for Space Telescope has HST, JWST data, and a bunch of other missions as well. This is basically a prototype, and it was basically my attempt to see how much can we do out of just, a little bit of experimentation here. So you can do things, for example, of asking your favorite star if there's any HST data for it, and you'll get some interesting results. So if you're interested to learn more, try it out, or just have questions about it, feel free to check out my poster. Thank you.
Hi everyone, I'm B. Pratip Day. I'm a postdoc at University of Toronto Statistical Sciences. So how many of you have wondered why deep learning works? Why can we fit a model to data where the number of parameters are more than the number of data points we have? These are the questions that we keep on discussing at the Astrophysics research team at U of T. And there's a lot of literature talking about this. And traditional statistical intuition is not wrong. We just need to reframe it. And a lot of research has been done. We thought that other people will also be interested in knowing this. So we decided to write a book on it. However, for us writing a book, it would probably take 10 years to finish it. So we tried to get help of AI agents to accomplish this. But we don't want AI slop. So we came up with this fairly complicated workflow of creating educational materials, which is long form, has trustworthiness built in, and human in the loop, those two humans. Built in, and so that we can audit everything, and while preserving our own ideas, our own voice in the whole thing. Was not to replace us, but to accelerate what we could do, try to finish this in 1 year as opposed to 5 years. So if you're interested in the book or the workflow, we can talk more about in the poster session in the afternoon. But happy to chat. Or what workflow was followed to make this poster. This is the prettiest poster I've ever made. But okay, chat with you later. Thank you.
Hello, I'm from the University of Portsmouth in the UK. I'm a second year PhD there. And here I'm presenting something called automatic construction of an extragalactic distance catalog. So basically, we found out that the distance catalogs out there are highly inconsistent with themselves. So we want to build a reliable tool for the distance ladder and for cosmology for things like the Hubble tension and other cosmological parameters. So basically, this is the pipeline. It consists of 4 steps. The first one is the document sourcing. So from all archive, we're going to determine all the papers which have distances to galaxies using an LLM. The second step is the rate extraction. which with using the text files from the papers in archive, we extract the distances using regex. This is kind of a little bit similar to one project in the last POP session, and it's quite interesting. We had a small chat, and there are similar things there, but also differences. For example, we use text files. They're using PDFs. So basically, we target for distance modulus. For example, some people quote it like /mu or lowercase m minus capital M, or other ways. We're trying to make the code as general as possible. And we've looked for distances both in tables and text, and the errors. Like in tables, we extract the errors in the columns next to the ones quoting the distance modulus. And for the text, we look for the numbers after the plus minus sign. We also have cases for asymmetric uncertainties, like if they have a different lower and upper limit. And yeah, we also handle cases for systematics, statistical, total errors, and we send everything to extract catalog. The third step is to determine which of these distances are original from the paper, because a paper quotes a lot of distances. So which are original from the paper and which are quoted from the literature. So we're using an LLM to extract only the original and reliable ones. And finally, we use another LLM to validate the results. So if you have any ideas for this, I will happily listen to them. Thank you so much.
All right, thank you. I have 3 logistical items that I need to share with everybody. The first one is the most important piece of information you will get today. That piece of information is the buffet is 2-sided. So please use both sides to facilitate getting us all fed as quickly as possible. Item number 2, if you have dietary restrictions, please abandon your friends in the line, go find a caterer. Check with them about the food that they will be providing for you today, and then you can hop back in line with your friends once you have gotten that information from catering. And the last item, please come back here to this room, ignore what the schedule says, come back here to this room in an hour at 1:50. All right, go enjoy lunch.
How are you doing? No.